Hello, everybody. My name is Madeline Mevis. I am a student at Arizona State University, and I will be presenting my research on locomotive adaptations in Diadectes and the Gopher tortoise. I will begin with giving a little bit of background and history on some of the clades, species, and time periods that evolved before our species of interest. I will begin with the Devonian period. The Devonian period was 419 to 359 million years ago and was a time of warm climate, higher atmospheric carbon dioxide levels, and high sea levels. In this period, the first forests developed, terrestrial arthropods flourished, and a vast number of fish emerged. Thus comes the first Sarcopterygiae to evolve, which is the lobe-finned fish. The ocean is packed with vast wildlife, has high predation, and high competition for food sources at this time. Which brings us to our first species of the Devonian, the Ellipsostegids. This species still possessed some ancestral locomotive features such as ray fins. However, they had adapted new features such as no dorsal or anal fins, bony elements in these limbs that connect to the pectoral girdle, which is disconnected from the skull. The pectoral fins have moved to the bottom of the animal and they had projecting ribs. I believe these locomotive features evolved due to the high concentrations of predation in the marine environments during the Devonian period, which would give the species the ability to escape into shallower waters. I also hypothesize their pectoral fins adapted to be underneath the body instead of on the sides because it would give them an advantage for lifting their head and locomotion to assist in hunting and escaping predators in shallow water. Next, that brings me to the Tiktaalik. Tiktaalik existed 385 million years ago, also in the Devonian period. This species experienced skeletal changes such as the loss of extrascapular bones as well as opercle and subopercle bone. Tiktaalik also had bendable pectoral fins for lifting their head out of water and locomotion through shallow water and coastal areas. I hypothesize these features are advantageous adaptations for reducing prey competition and for inhabiting shallow areas. To the left, you can see Tiktaalik pictured. Next, we arrive at the late Devonian. Forest development during the Devonian led to increasing oxygen levels and decreasing carbon dioxide levels in the atmosphere. Thus comes a global cooling glaciation event, leading to lowering sea levels in the late Devonian. The developing plants and forests during this period led to an overgrowth of algae bloom that ultimately attributed to oceanoxia in the late Devonian. Which brings us to our next two species, the Acanthostega and the Ichthyostega. Ichthyostega and Acanthostega evolved in the late Devonian and retained ribs like their predecessor, the Tiktaalik. However, they did evolve digits as well as a pelvis and a scapulocoracoid. All these developments would have been advantageous adaptations in lifting their mass against gravity to support their bodies on land. Their newly bendable elbows and further developed limbs would be advantageous to escape predators in the water, key for accessing oxygen-rich air, and useful for catching terrestrial prey. Especially considering there was oceanoxia at the time these species developed, this environmental pressure would have been a key evolutionary driver for these limbs to develop and to be able to come up onto terrestrial land or breathe atmospheric air. If you look to the left, you will see how these skeletal features in the Tiktaalik further developed in the Acanthostega, with limbs and digits developing, and the Ichthyostega developing enlarged ribs and pelvis. Next, we arrive in the Carboniferous period. The Carboniferous period began in the Mississippian period when Pangea was not fully connected. This marked a time of greenhouse climates globally, with rising sea levels from glacial melting flooding coastal areas of continents. Plant life thrived in terrestrial regions during the Carboniferous, and new terrestrial species began to emerge. Which brings us to the reptilomorphs and one of our species of interest today, the Diadectes. Reptilomorphs began to appear in the Carboniferous period all the way into the early Permian period and are completely terrestrial. Their locomotive adaptations that they evolved include additional digits on their front and back limbs. This would have been advantageous for balance and for grip in terrestrial locomotion. I hypothesize that these digits formed due to the terrestrial environment pressures for locomotion and access to more available food and oxygen. Next, we arrive at the tetrapods. Now, we've already talked about some of the early stem tetrapods. Early stem tetrapods began in the late Devonian and continued to evolve through the early Carboniferous period. Tetrapods proliferated in the Carboniferous period and the early Permian period and evolved further. It is hypothesized that the Carboniferous tetrapod diversification in Euro-America was propelled by a tropical rainforest biome collapse during this period. Which brings us to the development of amphibians. Amphibians are some of the earliest true tetrapods and are non-amniotes. Some features they have evolved are a loss of gills and developing subcutaneous respiration. I hypothesize the development of subcutaneous respiration was crucial for locomotion and was adapted from the environmental pressures of terrestrial breathing due to their recently adapted terrestrial or semi-terrestrial inhabitation. This increased oxygen intake upheld and supported the terrestrial locomotion needed. Which brings us to amniotes. Amniotes appear in the Carboniferous period with some of the earliest track records dating them to 358 million years ago in the early Carboniferous. There are two main lineages of amniotes, which are synapsids and sauropsids. The earliest fossil record outside of tracks trace these amniotes back to the late Carboniferous period and the beginning of the Pennsylvanian. I hypothesize that the evolution of the amniotes and the amniotic egg was driven by their terrestrial locomotive lifestyles and the need for gas exchange and developing offspring best suited to their newly adapted terrestrial environment. Rib expansion and coastal ventilation also evolved in amniotes. This is adapted to support the skeletal and muscular elements needed for locomotion as well as for oxygen needs for locomotion in this new adapted terrestrial habitat. Next, we arrive at reptiles. Reptiles are amniotes and of the sauropsid lineage, first appearing in the Carboniferous period. Body and abdominal muscles further developed and evolved for locomotive advantages in terrestrial environments for this species, as well as utilized for breathing. Ribs and muscles are used in conjunction with the gastralia for locomotion to move the animal forward. I hypothesize that this is evolved due to the terrestrial environmental habitats which these animals evolved. These further developed bones and muscles in reptiles was beneficial for locomotion in rougher or drier terrain. Which finally brings us to our next group, the testudines, and one of our species of interest today, the gopher tortoise. Testudines are reptiles with shells which evolved during the Triassic period, which was a very warm and dry period that was also marked the beginning of the breakup of Pangea. Testudines, or turtles, can be aquatic or terrestrial. Physical adaptations of turtles is tied to their environment of evolution. Terrestrial tortoises have higher shells in comparison to aquatic or semi-aquatic turtles. Aquatic turtles have specialized webbed digits on their limbs for locomotion, adapted for propulsion in the water. The gopher tortoise is a terrestrial burrowing turtle that evolved in the late Pliocene, and its fossil dates to Florida 10,000 to 120,000 years old. Some of the gopher tortoise adaptive features are its front limbs, which are paddle-shaped for shoveling dirt for burrowing. I hypothesize that this was an adaptive feature to avoid environmental predation and ensure more successful reproduction. And that brings us to the end of my presentation. Thank you so much for watching.